All right, so what I'll do now is review or provide the solutions to quiz 3. And with whatever time we have left over, we can just do a general review for the final. But there's nothing that I haven't said that you need to hear in order to be prepared for the final. So I don't have anything that I can only at this point repeat, which I'll do. Of course, I haven't presented the solutions to quiz 3 yet, so let's start by taking a look at that. All right, question 1 is to implement this function is strictly decreasing. You can see that this is a function that returns a Boolean value, so true or false.
Professor, can you switch the input on the projector?
Oh. Okay, got it. Thanks. As you can see, this is problem 1, and we have a function is strictly decreasing. And so it's called a predicate function. A predicate function is simply a function that returns true or false. And a predicate is like a statement. It's a statement that can be determined true or false. So the statement is the vector v is strictly decreasing. Is that true or false? So we return true or false as the return value. And you'll see here the vector is being passed in as a variable v. It's passed in as a constant reference. So that's when we refer to it as a reference, that means we don't make a copy of it. So we achieve an efficiency there. If we didn't have that reference symbol there, the function would end up making a copy of e when we come in, and execution enters the function. That would be an unnecessary copy. We don't need to make a copy, so we're just going to work on the original function that the caller passes into us as a reference. But we're going to promise to the compiler that we promise not to modify the vector. So we're just going to, we only need read-only access to the vector. So this is what this keyword const does. It makes that intention clear to the compiler. If we have code in there that tries to modify v, the compiler will issue an error and will refuse to compile the program. All right, let's go ahead and get this thing implemented now. So basically, we want to examine this. So we want this to be strictly decreasing. So we want to examine each element and make sure that it is it's larger than the element that follows it. So we're going to be scanning through the vector, looking at each element. So we'll need the appropriate sort of construct for that would be a for loop. Let's start at the first element, and let's continue while we don't want to go past the end. Let's continue while we're less than v dot size, and I'm going to put a -1 there, because we don't want to go all the way to the end. We're going to, at each element I that we look at, we're going to look at the element at I plus 1. So is the element at I greater than the element at I plus 1? So for that to make sense, we have to stop. I has to stop at 1 before the last element. So v has to stop at the last value that v takes on must be v dot size -2. So this is an equivalent expression. This is just a review here. So v dot, if you look at it like this, v less than or equal to size, then we see explicitly that the last value that I takes on is v dot size -2. Remember, counting in the indices start at 0. This is the index for the second to last element. But this is not what you typically see. You would typically see this. It's just kind of like a convention or a habit that you see programmers follow. Although the other expression is valid and fine. So here's our for loop. And so for each I, we're going to look at the value at I and verify that it's bigger than the value following it. But now this expression isn't going to, and I wrote it like this incorrectly because it's just a point of possible confusion, I guess. This isn't going to get us anything. This means that that a value is bigger than the value that follows after it. And but we wouldn't want to. This is good. This is what we're looking for. This means we're strictly decreasing, but we can't do this. This means we're going to exit the loop in the first good pair that we find. So this is actually the opposite of what we want. So what we need to do is pass through the entire sequence and checking that our condition holds, which would be and checking for our condition to fail. And then when our condition fails, then we return false. So the condition that would fail would be this. So if in fact we had a pair of numbers where the second one was greater than or equal to the first one, that means that the vector is not strictly decreasing, so we return false. And if we pass through all of those pairs, we don't return false. That means we are going to return true. All right. Let's look at the next one here. Write test code that tests every statement in the is strictly decreasing function. So that means we need test code that's going to run this and run this. Of course, if we get here, that means we're going to run this, and we're certainly going to run this. So we want to make sure, essentially, that we have test code that ends up returning false from here and returning true from there. So we'll have a vector v, and let's push back a value, 7, and we'll push back, say, 12 and 30. And here's our assert statement. Assert that we want to assert that this is strictly decreasing. So I got that wrong, didn't I? So this should be 30 here, 12 and 7. And now let's push on a bad value. I'll push on, say, 9. And then we can do this. Oops. And maybe if this is easier to read, we could do it like this. So that's a good test. That's a sufficient test to answer the problem. I don't know if it's sufficient for testing to do a complete test, but it does answer the problem. This test will test every statement in the program. And did I get this right? I'm going to go back and check that. So this is, like I'm taking the test, okay? I got to get this right in my lecture, so I'm going to go back to this and I say, let me think about this. I need to find a bad pair. So a bad pair means that that we're not strictly decreasing. We're not going down. We're going up. So does this show that we're going up? Yeah, if v of I is less than the value after it, then we're going up, we're increasing. So yes, that's where we return false. All right, so I checked my work, and I encourage you to check your work when you're taking these tests. Okay, here's the next one. Write a function named append that takes a vector of integers for its first argument and appends it and appends onto it every integer contained in an array provided as the second argument. All right. Basically, everything that's in A we want to append onto V. So the only way that I can think of doing it is to just call a push back for every value that I find on A. That means I have to look at every value in A. That's a loop. So values in A start at index 0, so I'll start my index I at 0. It has size many values, so I'll use that as my limit. And we just, whatever we find in V, whatever we find in A, we push it onto V. There it is. Any questions on that one? I think they're all pretty straightforward. Yeah, it's hard to read. They're, it's like doing word problems in math. You have to think about it and translate, those words and concepts into to code. All right, here's the next one. Implement a function called compute total that uses a loop nested inside another loop to compute the sum of all the values in an array, it should be an array, passed into the function as its first and only argument. The declaration of the function is shown in figure 3. The variables, rows, and calls are constants defined elsewhere in the program. You can see compute total returns a value, a double precision floating point number, a floating point value. And the array is, so that makes sense because the array contains doubles. So use a loop nested inside another loop. And these loops, we know exactly how many rows and columns we have, so we can use a for loop for this. So we need some kind of an accumulator that we use to add each value that we find. Something like that. Well, that means that sum needs to exist. So let's declare that. And we need to initialize it to 0. Unlike other languages, there's no default initialization, so we need to explicitly assign a 0 to sum when we define sum. And then, then we return sum. That's the return value. Maybe sum is, it says compute total that uses the loop. So, you know, maybe a slightly better program would be written with the word total, because that would match with the name of the function that we're implementing. This is a little bit more readable. Now I don't have to sort of match the word sum with the word total. I'm using the same word inside the code and in the name of the function as well. Okay, let's see, let's check this here. Let's look at the next one. Implement a function that replaces a vector in a vector every occurrence of the number 13 with the number 7. Okay, so scan through V. Whenever you find a 13, replace it with a 7. So we have to look at every number in V. So once again, we have another loop. And index starts at 0. And it goes up to, but doesn't hit size, just one before size, the last value it takes on. And then we'll have the condition now if v of I is 13, then v of I gets a 7. Maybe that's a little hard to read. If you want to be sort of consistent with the way I've been writing most of this code, I would probably do it like this. Makes it a little bigger. Takes up more space, but maybe it's easier to read. So this is how to assign a value. So we're talking about vectors that, you know, it's a sequence of storage locations. And we need to examine each storage location compared to the number 13. So you use the comparison operator, which is double equals. And if you find a match, then you want to use the assignment operator to store the number 7 in that storage location. And this is the syntax to do that. This says the storage location that is the ith index in V, that storage location, write into it the value 7. Okay. Let's look at the next one. Implement a function that searches for a given value in a vector of integers. If the value is found, the function returns the index of the value in the vector. Otherwise, it returns -1. So here we have search. The value that we're looking for is passed in as k. And we need to see if K is in V. Actually, V could contain more than one instance of K. And but we're just, so I didn't specify, I didn't sort of say return the first instance if it's found, but I could have written it like that. All right, so once again, we're going to need to look through V and try to find K. And it looks a lot like this one up here, doesn't it? It looks just like this one. We need to go through V and we're looking for K. Look at that. Look how similar that is. Scan through V and look for K. If we find K, what do we do? Return I. That's good, thank you. Return I. That's the index of K in V. And if we finish the loop and we never find K, then it's not there. So we will return -1. There it is. Okay, binary search. Implement a function that uses binary search to search for a given value in a vector of integers whose elements are in strictly increasing order. If the value is found, the function returns the index of the value in the vector, otherwise it returns -1. All right, let's do this one. So this is the binary search. It's different than the search that we just implemented. We had to look at each value. So we had a vector with 1,000,000 items in it. We'd have to see that K was not in there. We would have to do 1,000,000 comparisons. But if we knew in advance that the 1,000,000 values that are in V are in sorted order, that they're in increasing or decreasing sequence, then we don't have to look at each of the 1,000,000 items. We can use a binary search, as if we were searching through a telephone book without having to look at every single page to know that a given name was not in the book, or to find the name if it were there. So we're going to take advantage of binary search. Actually, the time it takes to find a value using binary search is proportional to the log of the size of the sequence. So it turns out to be a much smaller value than a search that's proportional to the number of values that are in the sequence, which you would have to do if things were not in sorted order. All right, so let's take a look at this. There's a start index of 0. There's an end index of v.size -1. And I'm going to use pseudocode here, mixed with a little C++. So we've got a start index, we have an end index. And now we're going to calculate the midpoint repeatedly, checking to see if K is at the midpoint. And we're going to go left or right depending on whether the value we're looking for is less than or greater than the value at the midpoint. So while S is less than or equal to E, I don't have to figure it out now because I figured it out in lecture. That S less than or equal to E works nicely. So while the start index is less than or equal to the end index, so if S equals E, that means m is going to be s, and we're going to just check the number that we're at. So let's check that now. So if, we need to calculate m. So m equals the average of s and e. That's our midpoint index. And if s and e were equal, then we would just get s or e. We would get, because they're the same, we would just get s. And now we can check to see that if v of m is the value we're looking for, then we're going to return the index. We need to return the index of k in v. What's the index of k in v here? What is the index of k in v at this point in the algorithm, if this if condition is true? It's m, okay. And else if the value at m is less than k, if the value of m is less than k, that means k is big compared to the midpoint. So that means I want to bring the start up to the midpoint. But we can go one past the midpoint. There's no reason to leave start at the midpoint because we just checked it. And also we need to go +1 so that we violate this condition and exit the loop. And so if neither of those conditions holds, then we need that means that v of m is greater than k, and therefore we have to set e to be m minus 1. And if we get to oh, actually we have to test this. This is yeah, that's right. So that's fine. So after we do this adjustment, let's suppose that s and e are equal to each other, and v of m is not k, so this is false. And then either s becomes large, or e becomes small, but then the loop condition fails. And at that point, we know that there's no more midpoint to calculate anymore. That's what we know it's not there. So we return -1. Is that hard to read like this? It's not exact. Now it's leaving the realm of pseudocode at this point to turn it into this. But I think it's easier to read. It's up to you how you want to express it. This is fine what I'm doing, or leave it the way I had it. It's okay. Is that easier to read? Who thinks that's easier to read? Looks like a majority on that. But it does take up more space. Okay, that's the binary search. What about this function, r identical? So A, B, and C. Write a predicate function that checks whether 3 vectors are identical. In other words, they contain exactly the same elements in the same order. So this is a variation on the problem that you had solved already. And so let's take a look at this. So there's two parts to the solution. First, we want to check to see if they're all the same size. If they're not the same size, we're going to return false and not bother to do any looping. We don't need to check the value of the elements in the vectors because they have different sizes. So the loop can't be written, without going past the end of the shorter vector if we don't check the sizes. That's another reason we need to start by checking the sizes. So let's look at it. So if, and there's more than one way to write this. If the size, if A dot size is not equal to B dot size, or so now let's suppose that A dot size doesn't equal B dot size. The compiler will generate code that will ignore everything else in that OR condition. It won't even bother to evaluate this part of the expression. If the left part of the expression is true of an OR statement, of an OR operation rather, then the right-hand side of the OR operation is not evaluated, and that's called short-circuiting. And you'll see this technique used a lot in code. This is something that actually when you're reading code and writing code, you have to be very aware of. And so if A dot size is not B dot size, then we're done. I mean, let's just return false. We don't even have to, we don't care about the rest of that. We know that we're violating the criteria of the criteria. So let's return false here. But let's suppose that that A dot size actually equals B dot size. Oh, so that's then that means this is false. This part of the OR operation is false. So the system says, well, I don't know it. The whole condition may still be true. The first part is false, but it's an OR operation. So that means we need to evaluate the right-hand side. So what do we want to? We know that A and B have the same size, so we can compare A dot size to C dot size, or equivalently B dot size to C dot size. It doesn't matter, right? So you take your pick. Sorry, to C dot size. That was it. So A and B have the same size. Doesn't matter which one we pick to compare to C. Now, and so we don't want equal there. We don't want unequal. So we're just trying to decide whether we want to, make an early decision without looking at the elements. Just return false if these are not identical. So if A and B have different sizes, they're not identical, return false. If A and B have the same size, oh, now we got to evaluate the right-hand side of the OR operation, and which is to compare the size of A to C. And if they're not equal, then we'll return false. But if both of these are false, that means the entire condition is false. And so we do not return false at that point. So we don't return false, it means they're all the same size. There's another way to do this. We could do it the other way. We could say, if A dot size equals B dot size and B dot size equals C dot size, then, and then we can have a block of code which then contains a loop that loops through all of the vectors and checks that their individual elements are matching. So we could write it like that. We could do it like that. Maybe this is hard to read or understand, and you'd rather write it the other way. That's okay. But see, the other way, I chose this way because I know the other way I would need to have a loop inside of the body of an if statement. So I would get an extra level of indentation. And my habit is to try to minimize the number of indentations in my code. But maybe it makes the Boolean expressions a little more difficult to understand. So there's a trade-off there. All right, let's see now how we're going to do this. We only need one index. And we're going to arrange that index. So they're all the same size, so we only need one index. Well, that's not the reason we need one index, but we only need one index. So we're looking at the values in A, B, and C at that one index. So once again, we're going to follow the same pattern here. We're going to check for violation of the criterion that all the values are the same at each position in the three vectors. So if we get violation of that criterion, then we're going to return false. So if we get some violation at position I, we'll return false. And if the criterion never fails and we finish the loop, then we know that they're the same. So we'll return true. Now, how do we check for failure for that equality criterion? How do we do that? It's going to look very similar to this. We're going to check the value in A at I. It's very similar to this. So I'm just going to copy that down there. We're going to check the value in A at I. If the value in A at I is not equal to the value in B at I, then return false. So we don't even need to look at this part here. We can just, at that point, we know that, oh, it's done, we got a bad match there, let's return false. Otherwise, if that's false, we need to look at the next, we need to look at C to see if the criterion fails on comparing the value of at I in A and C. There we go. That's it right there with my long-winded explanation. I don't know if my long-winded explanation helps, but I gave it to you. But yes, question.
Would it matter if it's or instead of and? Because if one of those is true, then it's going to return false, right? Because it could be either or.
Yeah, that's right. So A and B, they could match. You could have a 7 in A, a 7 in B, and a 3 in C.
But if you use or both times, would it A dot size and B dot size be the same size, and then their inches are the same? Like if those two are identical, then it would just return true, and then check C.
Wait a minute. You're saying that, let's suppose that A and B have the same size?
Like, let's just say A and B are identical. Then it would just return true, right? Because it didn't have to check for C because we used or, right?
You're talking about up here?
Yeah, like...
wait, let me slow up there. So let's suppose the test case here is that A and B are in fact identical, but C is different. Mm-hmm. Is C different by virtue of having a different size or by virtue of having different elements?
I don't think it would matter in this case.
So let's just take different size. Okay?
Size, yeah.
Let's take a different size. Let's do it like this. Let's suppose that A is size 2, and B is of size 2, and C is of size 3. Okay? Then this is false, right? Because 2 is not equal to 2. That's a false statement. So, and this is true. Because 2 does not equal 3. Yes, it is true that 2 does not equal 3. So either the first one is true or the second one is true. That's what I need to return false. And in fact, what we have here is the second one is true. So now we're going to return false.
Oh, so it doesn't matter if one of them, as long as one of them?
Yeah, just one. So we're only looking for one to break the rule.
Because I thought if how I read 4 is if the first one is the same size, then you're like, okay, it's the same size, and you don't have to check. Because it's like either or, that's how I was thinking of it.
Well, no, let's do it like this. Let's look at the solution where we use equality instead of inequality. That might kind of help you grapple with it more easily. How would we do it like that? Suppose that if A dot size equals B dot size, righty? It's easier to think about equality than inequality. If A dot size equals B dot size, we're not going to use OR here, and B dot size equals C dot size, then it's like, yeah, we're ready to go. And but we don't know yet because we didn't look at the individual items. But what happens if this is bad? What happens if we're not ready to go? But there's a difference there. Oh, well then we don't do anything inside. We do it out here. Because inside this logic in here, somewhere in here, we're going to end up returning true. So if this isn't true, that means we never enter this phase of our reasoning. And in fact, we know at this immediately that, well, we're going to return false. And maybe what helps with people, some people, is they like to see that as an else, actually. So if the first part is true, that means, hey, we're maybe there's a chance that we're identical. We have the same size, so we're going to need to do additional analysis here. But if this is not true, there isn't a chance. We don't have a chance of being identical at different sizes. We're going to return false. Now the question is, how do we, after we know that all three have the same size, how is the logic going to, be expressed at this point? Well, we got to look at each, individual value. So we're going to have that loop. I'm just going to grab this here. Save a little typing. Get rid of that for now. So we're gonna range through, A, B, and C. They all have the same size, so we could just use A dot size. And now what are we going to do in here? Let's suppose we want to keep it in the positive. So we say if A of I is B of I, well, that's not good enough, right? That means, yeah, that's good. That's good. We need that. And we also need that B of I is C of I. And so that checks out. That means I is good. The values at I match up, and that's great. But if the values at I don't match up, then which is the else condition, then we know at that point, then and there, we know that we don't have identical vectors. So we're going to want to return that. But what do we do here if, in fact, we know that they're the same at that point? Well, there's nothing to do. We just say, well, this step is okay. Now let's go and look at the next one. We can't make a conclusion at this point. That's why it's easier. You see, this code is getting bigger, and if you use the negative approach, the code is more compact.
Could you still use like the and instead of or with the sustained division?
Up here?
Yeah, could you use and there too, or no?
No, we cannot use and here. Because let's suppose we had and here. That means that, see, look, A is 2 in size, and C has size 3. That means this part is false. I'm sorry, that part is true, right? This part is true, and this part is false. This part is false. Wait, you wanted to use equality? Or you're talking about using and.
Yeah.
Okay, so this part is false. 2 not equal to 2 is false. 2 is 2. So A dot size is 2, B dot size is 2. So that we're saying in this expression, it's 2 does not equal 2. So that is false. So if this is false, we don't even have to look at this part here. We know that the whole thing is false. If the whole thing is false, we don't execute the body of the loop. We don't return false, but we should. We should return false.
We can change that A dot size instead of A dot size, you can do B dot size is not equal to C dot size. Then you can return false.
Yeah, but that doesn't. Of course that works, but then then I can just change these values.
On the other one, on the other part, after the and thing, if you keep A dot size is not equal to B dot size and B
Wait. And
B dot size is not equal to C dot size.
And B dot size is not equal to C dot size.
Then you can return false.
But we don't, the thing is this, the compiler generates code that will never evaluate this part of the expression, because the left-hand side of that AND operation already returns false. So the whole thing is false. See, if it doesn't matter if the right-hand side of that expression is true or false, if the left-hand side of this AND expression is false, it doesn't matter what's on the right-hand side. The whole thing is false. If there's one bad apple in the barrel, the whole barrel's bad. That's the idea. Are you convinced?
Like doing truth tables, right?
Yeah, you got to use truth tables. You got to think about it. How many people took symbolic logic in here, by the way, like the GE course, symbolic logic? Can I see show hands?
So in a truth table, though, if you have a true or a false, then it's a true statement. Because one of them is true.
That's right. That's
So
right.
how could we return false if you're doing an or statement? So if you have a true or a false, then you have a true statement.
Yeah, so they both need to be false.
Yeah.
They both need to be false. We want A does not be, A is not B. That has to be false. B dot size is not C dot size. That has to be false. The claim is that A and B are different in size, and B and C are different in size. Both of those claims must be false, so that we have a false or false to give us a resulting false. Because we want a resulting false. If we don't get if we get a resulting true, we're going to return false. For those people who took symbolic logic, did you find this, did that class help you to think through these problems?
That's what I used kind of for this
Yeah.
problem. That's why I asked if there's a difference between or
Discrete
and.
math? Yeah.
Because if you're showing if you show AB, BC, then that implies AC. So that's what I used to do this problem.
Yeah.
But I didn't know if there's a difference between
Well, you know, this is the alternative approach here. But actually in here, there's nothing that you need to do in here. I put a question mark in there, but you just do nothing.
Thanks for clarifying.
Yeah. At a certain point, I won't be able to explain it. You got to sit down and think about it quietly. Okay. That's it, right? Oh yeah, I was ready to do sort, but I'm not going to do that. Sort is on the final. There's no surprise there. I'm going to ask you to write down the sort algorithm, some sort algorithm, the one that's natural to you, the one that you figured out on your own. That's the optimal. If you can sit and figure out a sort algorithm on your own, test it on your own, like in lab for the lab assignment, and then show me that sort algorithm that you know intuitively, that you have, you know, that you've come to know through your own creative thinking. And that's the best to do. The second choice is just to memorize what I wrote down in lecture. You know, and you're not going to learn much that way. But if you want to just get the score, then you can do that as well. But sorting, I will ask for sorting. And I'll also ask for binary search as well. So those are guaranteed to be on the final. Are there any other questions? Okay, I guess that's it. There is lab today, so I will be in lab. And if you want me to work with you individually, I'm available for that.